Good morning, students.
Good morning, ma'am.
Good morning. So, in our previous class, we discussed the AC voltage through capacitor and we derive expression for the current that is generated in an capacitor whenever it is connected to an AC voltage source. So, first of all, we can recollect all these points regarding with a resistor, inductor, and capacitor. After that, we can derive the expression for power developed in the capacitor when it is connected to an AC voltage source. So starting with Naurin. What is the equation for current developed in an capacitor when it is connected to AC voltage source?
Im sin omega t plus 90.
I is equal to Im sin omega t plus 90 in terms of cos function.
Im cos omega t.
I is equal to Im cos omega t. Then the equation for current in the case of inductor.
Im sin omega t minus 90.
I is equal to Im sin omega t minus 90. Achut, in case of resistor. Value of current in case of resistor.
Im sin omega t.
I is equal to Im sin omega t. So we derive the expression for current developed in the electric circuit when it is connected to all the three different components. In the case of resistor, the current is I is equal to Im sin omega t. In the case of inductor, it is given by I is equal to Im sin omega t minus 90. In case of capacitor, we have I is equal to Im sin omega t plus 90. Okay. So today we are going to describe an expression for or derive an expression for power developed in a capacitor. Did we derive the expression for power in case of capacitor? Okay. So let us see what about the value of instantaneous value of power in a capacitor when it is connected to an alternate source of EMF. V is equal to Vm sin omega t. So all of you write the next heading. Power developed in a capacitor. Power developed in a capacitor. What is the expression for calculating the power? The general expression P is equal to
VI.
VI. P is equal to VI is the general equation for calculating the power. P is equal to VI. But here we are going to calculate the instantaneous value of power. That is P instantaneous is equal to. In the case of a capacitor, we are applying or we are giving an alternative source of EMF. V is equal to Vm sin omega t. So here in the case of a capacitor, the voltage V is equal to Vm sin omega t. And what about the value of the current generated in a capacitor when we connect this alternate source of EMF? V is equal to Vm sin omega t. Value of current in terms of cosine function. The original current generated in a capacitor.
Im cos omega t.
I is equal to Im cos omega t. So the general expression for calculating the power is given by P is equal to Vi. But here we are deriving the expression for power in the case of a capacitor when it is connected to an alternative source of EMF. V is equal to Vm sin omega t. When we connect an alternative source of EMF, V is equal to Vm sin omega t, it will generate a current that will be equivalent to I is equal to Im cos omega t. So the expression becomes P instantaneous is equal to, instantaneous value of power is equal to Vm sin omega t into Im cos omega t. Or we can write P instantaneous is equal to Vm Im sin omega t into cos omega t. What is sin omega t into cos omega t? Sin 2 theta into cos 2 theta. In trigonometry, what is the value of sin 2 theta into cos 2 theta? Or sin theta cos theta. You don't need to be worried about sin 2 theta and cos 2 theta. Sin theta into cos theta.
Sin 2 theta.
Sin 2 theta or 2 sin theta. Sin theta into cos theta.
Sin 2a by 2.
Yeah. So if the in trigonometry, if we have sin 2 theta into cos 2 theta, we can write 2 sin theta by 2, right? Or sin 2 theta by 2.
Sin 2 theta.
Yeah, sin 2 theta, that is equal to sin 2 theta divided by 2. Similarly, here we have another phase angle omega t. So instead of sin 2 theta cos 2 theta, here we have sin 2 omega t, sin omega t cos omega t. Sin omega t cos omega t. So it becomes sin 2 omega t divided by 2. So the instantaneous value of power becomes P instantaneous is equal to Vm Im sin omega t cos omega t. It becomes sin 2 omega t divided by 2. Instantaneous values of power becomes Vm Im sin 2 omega t divided by 2. Or we can write instantaneous value of power P instantaneous is equal to Vm Im divided by 2 into sin 2 omega t. This is the expression for instantaneous value of power that will be generated in a capacitor when it is connected to an alternative source of EMF. V is equal to Vm sin omega t. So here we are starting from the general expression for calculating power. P is equal to Vi. Then the instantaneous values of power is given by the value of applied voltage to the capacitor into the current generated in the capacitor when it is connected to an applied source of EMF, alternative source of EMF. V is equal to Vm sin omega t. So it becomes P instantaneous is equal to Vm sin omega t into Im cos omega t. We just rearrange the equation. So we get P instantaneous is equal to Vm Im into sin omega t cos omega t. So this sin omega t cos omega t is in the form of a trigonometric equation, sin 2 theta cos 2 theta. So we can write sin 2 theta divided by 2. Similarly, here instead of 2 theta, we have another phase angle omega t. So the expression become instantaneous value of power is equal to Vm Im into sin 2 omega t divided by 2. Then we just rearrange the equation. Instantaneous value of power is equal to Vm Im divided by 2 into sin 2 omega t. So what is our next step? Here we obtain the value of instantaneous value of power. What about the next value we want to find out from here, from this value?
Average power.
Average value. Therefore, average value of power is given by average value of power. It is represented by P bar. P bar is equal to, can you form an equation for calculating the average value of power? Exactly similar to that of the case of inductor. P bar is equal to, unmute and say,
Vm Im by 2, then summation of sine
Vm Im by
2.
2 into summation of sine 2 omega t. Right. Then, so this is the equation for calculating the average value of power. We just take the summation of sine 2 omega t term. So average value of power P bar is equal to Vm Im divided by 2 into summation over sine 2 omega t. Then what about the summation of sine 2 omega t?
0.
That is equal to 0. So the average value of power in the case of capacitor becomes P bar is equal to Vm Im by 2 into 0. That is equal to 0. So in the case of capacitor also, here we have the average value of power P bar is equal to 0. Okay. So once again, I will collect all the equations regarding with that of the AC voltage through capacitor. AC voltage through capacitor. Vidur expression for voltage in the case of capacitor.
Vm sin omega t.
V is equal to Vm sine omega t. Okay, then Sania expression for current. In case of capacitor, expression for current.
Im sine 9v plus omega t.
Im sine omega t plus 90. Okay, then Anna expression for power.
P equal to Vm sin omega t into Im cos omega t.
Final expression for power.
Vm Im into sin 2 omega t by 2.
Okay, Vm Im by 2 into sine 2 omega t. This is the expression for instantaneous value of power in the case of a capacitor. Then Mehak expression for average value. What is the average value of power that is developed in a capacitor? Average value. Alvin, what about the average value of a capacitor? P bar. That is what is we are discussed now. Evelyn, average value of power?
0.
0. Average value of power in the case of a capacitor is equal to 0. So these are the equations that is connected with capacitor when it is connected to an AC voltage source of EMF. V is equal to Vm sin omega t. So in these three cases, whether we are considering the case of a resistor, inductor or capacitor, all the three cases, the applied alternating voltage will be the same, that is equal to Vm sin omega t. The same alternative source of EMF, V is equal to Vm sin omega t, is applied to all the three electrical components. But the current generated in each cases will be different. In the case of a resistor, the current generated is given by I is equal to Im sin omega t. Okay. In the case of a resistor, for resistor, current generated is given by I is equal to Im sin omega t. In the case of inductor, what is the value of current generated? I is equal to Im sin omega t minus 90. In the case of capacitor, what is the value of current? I is equal to Im sin omega t plus 90. Okay. And here we derive the expression for instantaneous value of power in the case of resistor, inductor, and capacitor, and what about its average value? Is there any doubt regarding with all these topics?
No, ma'am.
Okay. So now we can move to the next topic, AC voltage applied to series LCR circuit. All of you write the next heading. AC voltage applied to a series LCR circuit. What do you mean by LCR? LCR. LCR. What is L represents? L. No idea. What is this L
Inductor.
represent? Inductor. What about C?
Capacitor.
Yes, L is indicates inductor. C for capacitor. And what about R?
Resistor.
Resistor. So, first of all, we are deriving the expressions for inductor, capacitor, and resistor separately. We derive the separate equations for instantaneous value of power in the case of inductor, capacitor, resistor. And what about the current generated in the case of inductor, capacitor, and resistor and all. But now we are going to combine all these three components together. That is, we are going to connect the inductor, capacitor, and resistance in a series combination. Here we are going to connect all these three components together to an electric circuit, and we are going to apply an alternative source of EMF Vm sin omega t into this electrical components. Okay. So what is the symbol of inductor? How we are representing the inductor? Representation of inductor. What do you mean by inductor? What do you mean by inductor? Aditya?
I'm like the solenoid.
Yes, inductor means just like some solenoids. They are represented in the form of coils. Inductor are the devices that store the energy in the form of magnetic energy. So first of all, here we have considered an inductor. Then capacitor. Capacitor is represented by two parallel lines. And then we have a resistor. How they are combined? All these components are combined in a series combination. So the end of the inductor is connected to end of capacitor. The next end of the capacitor is connected to a resistor. Then to all these three components, here we are applying an alternative source of EMF. V is equal to Vm sin omega t. Okay, so this is represents L, C, R. So in the very beginning of the class, we discussed all the different cases that is happen whenever in the inductor or capacitor and resistor is connected to an alternative source of EMF, V is equal to Vm sin omega t separately. But now we are going to combine all these three components in an electric circuit in a series manner. The inductor, capacitor, and resistor is connected in series. And we are applying an alternative source of EMF, V is equal to Vm sin omega t into the circuit. So consider a series combination of inductor, capacitor, and resistor. Consider a series combination of inductor, capacitor, and resistor. Then connect an alternative source of EMF. Then connect an alternative source of EMF. V is equal to Vm sin omega t into the circuit. Consider a series combination of inductor, capacitor, and resistor. Then connect a series combination, an alternative EMF of V is equal to Vm sin omega t into the circuit. Or apply an alternative source of EMF V is equal to Vm sin omega t into the circuit or into the series combination. Is it over?
Yes, ma'am.
Okay. So here we consider LCR, inductor, capacitor, and resistor in a series combination. Students, you may please recall what are the characteristics of a series combination of resistors? Series combination. What are the characteristics of series combination?
Current is same.
Very good. So whenever an alternative source of EMF is connected to the circuit, the current is passing through all the combination, all the electrical components will be the same. The same current I is passing through the inductor, capacitor, and resistor. Then what about the next characteristics?
Potential difference.
Potential different is, what about the value of different? Potential difference V is different for different electrical components. So here VL is the potential through the inductor L. VC is the potential through the capacitor with the capacitance C, and VR is the potential through the resistor with the resistance R. So here we consider a series combination of inductor, capacitor, and resistor. Then we apply an alternative source of EMF. V is equal to Vm sin omega t into the series combination. Since it is a series combination, the current flowing through all the electrical components will be the same, but the potential difference is different. Or the voltage are different for different electrical components.
And can say it once more.
Okay. So here we are applying an alternative source of EMF. V is equal to Vm sin omega t into this series combination. Since it is a series combination, current through each electrical components will be the same. Current through each electrical components will be the same. But voltage through each electrical components are different. But voltage or potential difference through each electrical components are different. That is, VL is the potential through inductor L. VC is the potential through capacitor C. And VR is the potential through resistor R. Since it is a series combination, the potential through each electrical components are different. VL is the potential through inductor L. VC is the potential through capacitor C. And VR is the potential through resistor R. And here we know that the current is flows along the same direction. The same current is flowing through the inductor L, capacitor C, and the resistor R. The direction of the current will be the same. Then by applying the Kirchhoff law, we can say that B is equal to the sum of EMF through all the electrical components. Then by applying the Kirchhoff laws, we can say that V is equal to VL plus VC plus VR. By applying the Kirchhoff laws, we can say that V is equal to, that is the total voltage or the resultant voltage is equal to sum of the voltage through individual electrical components. That is V is equal to VL plus VC plus VR. Again, what is the expression for the potential that is stored or generated in an injector? Expression for potential generated in the case of an injector. VL is equal to, we know that in the case of a resistor, according to Ohm's law, VR is equal to, or V is equal to IR, current into resistance. The product of current into resistance gives the potential. Similarly, what about the expression for the voltage developed in a inductor? We studied this expression in our previous chapter, in electromagnetic induction. The induced EMF in an inductor or in a solenoid when it is connected in a for the expression for self-inductance, the EMF generated in an inductor or in a solenoid. VR is equal to product of current into resistance. So here R is the resistance, that is the resistance offered by the resistor to the flow of current. Similarly, VL is equal to L into di by dt. Sometimes you may be study this equation in terms of induced EMF E. E is equal to minus L into di by dt. But here this negative sign is indicates the direction of the electric current. So here we are not consider that negative sign. So the expression for voltage or potential that is generated in the case of an inductor is given by V is equal to L into di by dt. V is equal to, or VL is equal to L into di by dt. Similarly, what about the expression for the voltage generated in a capacitor? What is the equation for calculating the charge developed in a capacitor? Q is equal to charge developed in a capacitor. Q is equal to if you know the answer, unmute and say Q is equal to CV. So which implies what is the voltage that is passing through a capacitor or generating in a capacitor? Q is equal to CV, which implies V is equal to
Q by C.
Q by C. So here we get an expression for the voltage that is developed in a capacitor. VC is equal to Q by C, where C is the capacitance of the capacitor. Okay. So here we can substitute all these expression into this equation. So by applying the Kirchhoff laws, we have V is equal to VL plus VC plus VR. So give this equation number 1. But here VL is equal to inductance into current. Instead of resistance into current, in the case of VL, here we have an inductance. L into current di by dt. So VL is equal to L into di by dt. Similarly, VC is equal to Q by C, and VR is equal to the product of current I into R, IR. So we can substitute all these value of VL, VC and VR into equation 1. It becomes V is equal to, instead of VL, here we have L into di by dt plus VC. Instead of VC, here we have Q by C plus VR, that is I into R. So V is equal to L into di by dt plus Q by C plus IR. So this is the expression for calculating the voltage, the voltage that is generated in a series LCR combination. But here we want an expression for instantaneous values of power and that of the average value of power and all. So for that, here we have two methods. So this expression gives the value of voltage that is passing through inductor, capacitor and resistor when it is connected in a series combination, and an alternative source of EMF V is equal to Vm sin omega t is applied to it. But here we want the expression for instantaneous value of current. Okay, here we want to calculate an expression for instantaneous value of current and their corresponding phasor diagram, similar to that in the case of inductor, capacitor and resistor. So here we have two methods are there. Here we have two methods are there to find the instantaneous value of power. One is phasor diagram method. And other is the second one, analytical method. To find the instantaneous value of power and in order to represent the phasor diagram, we have two different methods are there. One is phasor diagram method and other is analytical method. Sort of these two, phasor diagram method is very, very important method in order to calculate the instantaneous value of power and the representation of series LCR combination in terms of phasor diagram. So we have two methods are there to calculate the instantaneous value of power that is developed in a series LCR combination when it is connected to an alternative source of EMF V is equal to Vm sin omega t. The two different methods, one is phasor diagram method and the second one is analytical method. So we can discuss these two methods one by one. So first of all, we are going to discuss phasor diagram method. Phasor diagram method. So here we are discussing the topic AC voltage that is applied to a series LCR circuit. We derive the expression for instantaneous value of power and the corresponding phasor diagram in the case of inductor, capacitor and resistor separately in different cases. But here under this topic, here we consider or we are combining all these three electrical components together and they are connected in a series combination. Then an alternative source of EMF V is equal to Vm sin omega t applied to this series combination. Since it is a series combination, the current is flowing through all these electrical components, that is through inductor, capacitor and that of the resistor will be the same. But the voltage that is developed across each electrical component will be different. So here we taken the voltage across the inductor as VL, voltage across the capacitor as VC and the voltage across the resistor as VR. Then by the Kirchhoff laws, we have V is equal to VL plus VC plus VR. Then we just recall all the equations for the potential that is developed in all these electrical components. In the case of inductor, the induced EMF in an inductor is given by an expression E is equal to L into di by dt. We are already derived this equation in our previous chapter, electromagnetic induction. So instead of the term E, induced EMF E, here we are giving the same term for voltage VL. VL is equal to L into di by dt. The second one, VC is equal to Q by C. This expression is also derived from the equations for capacitor. According to the equation for capacitor, here we have Q is equal to CV. From that, we can calculate the expression for voltage. V is equal to Q by C. So the voltage that is developed across the capacitor is given by V is equal to Q by C. Then the last expression for resistor, that is according to Ohm's law, we know that the voltage that is developed in a resistor is equivalent to the product of current and resistor, because voltage potential difference across the ends of a resistor is directly proportional to the current that is flowing through the resistor. And here this R is represents the proportionality constant. So VR is equal to IR. Then we just substitute all these values into the equation. It becomes V is equal to L into di by dt plus Q by C plus IR. So this is an expression for voltage. But here we want to calculate the instantaneous value of power that is developed in a series LCR combination. For that, we have two different methods are there. One is phasor diagram method and the second one is analytical method. So here we are going to explain the instantaneous value of power using the phasor diagram method. Is it clear now?
Yes, ma'am.
Okay. So the next one is we are going to discuss about the phasor diagram method. So in order to explain this phasor diagram method, first of all, we can recall the value of instantaneous value of current, not instantaneous, the value of current and the voltage in case of resistor, capacitor, and inductor. First of all, we just recall all these equations once again. In the case of resistor, what about the value of voltage? V is equal to Vm sin omega t. I is equal to
Im sin omega t.
Im sin omega t. Then in the case of inductor, V is equal to the same alternative source of voltage. V is equal to Vm sin omega t, but I is equal to I in the case of inductor.
Im sin omega t minus 90.
Im sin omega t minus 90. That is here the phase angle is given by omega t minus 90. So, okay. Then what about in the case of capacitor? Capacitor. V is equal to Vm sin omega t and I is equal to Im sin,
Plus 90.
yes, I is equal to Im sin omega t plus 90. So in the case of inductor, the value of current I is equal to Im sin omega t minus 90. In the case of capacitor, I is equal to Im sin omega t plus 90. And here we consider a LCR. We are combined this inductor, capacitor, and resistor in a series combination. We know that in a series combination, the current remains the same. Okay, the current remains constant. The same current is flowing through the inductor, capacitor, and resistor. The current will be the same. So we are going to represent the phasor diagram for voltage. Here we are going to represent the phasor diagram for voltage. In a series combination, since in a series combination, the current remains constant. Since in a series combination, the current remains constant. We are going to represent the phasor diagram with respect to EMF. We are going to represent the phasor diagram with respect to EMF.
Ma'am, can you tell again?
Okay, since it is a series combination, the current remains constant. Since it is a series combination, the current remains constant. So that we are going to represent the phasor diagram with respect to EMF or voltage. So that we are going to represent the phasor diagram with respect to EMF or voltage. And here, in order to represent the phasor diagram, first of all, we should have an idea about the value of current and EMF in the case of an inductor and capacitor. In the case of resistor, both the value of current, the phase angle, in the case of phase angle, in the case of resistor, the phase angle are the same. V is equal to Vm sin omega t and I is equal to Im sin omega t. Both of them are in the same phase. But what about in the case of inductor? The value of voltage and current, does they are in the same phase or in different phase? In the case of inductor, they are in different phase. And who is leads? Does the EMF is leads or current is leads in the case of inductor?
EMF.
EMF. In the case of inductor, EMF leads the current by 90 degree. What about in the case of capacitor?
Current.
Current leads the EMF. So we know that in the case of a resistor, both are in same phase. Both are same phase. In the case of inductor, we write a clue like ELI. Here EMF leads the current. In the case of inductor, EMF leads the current by 90 degree. And in the case of a capacitor, we know that current leads the EMF by 90 degree. Current leads the EMF by 90 degree. So here we are going to draw the phasor diagram. First of all, we are representing the voltage corresponding to resistor. Here in the case of resistor, the EMF and current both are in the same phase. So we can write VR. Here both are in the same phase. Now in the case of inductor, EMF leads the current by 90 degree. So we are representing a 90 degree with respect to VR. Here we have VR. Now this represents VL, EMF corresponding to inductor, VL. Here the voltage of this EMF leads the current. In the case of inductor, it leads the current, EMF leads the current by 90 degree. But in the case of capacitor, EMF lags the current by 90 degree. That is along minus 90. Okay, now it's the time I will explain the same topic in our last period.